Welcome everyone. Thank you for joining us on this presentation. I'm going to take you through the Multotec sensors and how they work at a very high level. It'll be fairly short, but there'll be time for questions at the end. So if we look at the big overview, we're looking at a connected plant for the future, and just as an example, I've put up a schematic of how a process plant might work. The blue dots represent sensors that could be fitted everywhere in the plant. They can go on any piece of equipment, multiple sensors, any equipment that's not shown here. Basically, any equipment that moves, and we want to find something about that, we can put one of these sensors on. And then the beauty of the system is with an entire connected plant from one piece of equipment all the way through the process to the end, we can see an amazing amount of information of what's happening with that equipment, but also with equipment upstream and downstream. So if we look at the good being what we have been successful with so far, we've done a lot of work on screen panel wear, and we've got sites running that are testing that and being successful at the moment. And so from a screen panel, which is equivalently to that sensor there on a screen, we're getting live fed data about the wear of that panel displayed on a dashboard on your computer. Other stuff that we've done, dynamics of the screen and maintenance of the screen, so stringers and cross members. In this process, we've proven that we can see all of those, and that's very useful information. In terms of cyclones, we've done quite a lot of on-site work and been successful in finding tramp in cyclones, and when the tramp comes into a cyclone and when it leaves a cyclone. A very interesting project was done on cyclones that block and why they block and what to do about the blocks. We've also done extensive work on wear on cyclones, the lining of the cyclones getting damaged. And a very interesting part is upstream misplaced material. We were able to detect that on a cyclone. So for instance, a screen like this was misplacing material because of a loose panel. It went down the process through the pump into the cyclone, and we picked up that misplaced material with a sensor on the cyclone. So it's not only required to be able to see stuff that is happening on the piece of equipment that is giving the problem, but you can see it further down the line with the effect that happens further down the line and what happens. And then obviously also pump faults. How do those look? You can pick them up down the side as well, but it would be, if you're looking for pump issues, it would be better to put a sensor on a pump. The stuff that we have proven in the lab is numerous. So we've done pegging in the lab on a simulated screen. We've done loose panels. This is a very interesting one where panels come loose. We can detect that pretty easily. We haven't yet had a panel come loose in the field, so I can't move that into the good, but we would be able to see that. Then the load on the panel, damaged panels. In terms of cyclones, we can pick up roping, we can pick up relative density changes, very small changes in relative density. In the lab, we found 2% changes in relative density, spigot wear, cut ratios, and on pumps, all the stuff that you want to see, the flow rates, the head, the power that the pump is absorbing, and therefore the overall efficiency of how the pump is working. What's the ugly? So what's not so easy? Getting the training data to verify the aspect of what you're looking for is sometimes not all that easy. In terms of pegging, when we're looking for training data, we don't know when it happens. So while screens typically shut down once a week or every 2 weeks, we don't know in that period what minute or couple of minutes, a rock got stuck in a hole on the panel. We can't predict that. So that's an example of where it's quite difficult to do the training on a live site. And so that's one of our big challenges, is doing that verification, because we need to feed the computer with correct information if we wanted to give us correct information back. The second aspect is the long implementation time. So sometimes you need to run through an entire set of or entire life of a panel, and you can only then predict on the second run as to what's happening with that panel life. So those are sort of two bad aspects. The third is finding value realization for the customers. So looking at the plant, where is the value actually in a report going to generate some benefit for the customer, and therefore benefit for us as a supplier. So those are the bad sides of it, but the technology is absolutely amazing. The ability or the amount of data that is in the movement is incredible. The stuff that you can detect is quite amazing. I use an analogy. We've all got step counters, or most of us have got step counters on our wrists. That's measuring your steps, but it's attached to your wrist. You can see an amazing amount of information of what's happening with you and your body by the way that your wrist moves. And an example would be, if you had a sore toe, you might limp a little bit. Your wrist would pick that up. And so in that movement is an example of any machine. The way that it moves is going to reflect what's happening to that machine. Just going through a little bit more specifics. So we use vibration sensors. There's the sensor there on a cyclone. It's a very small device. It's not invasive. It magnets on the outside. It doesn't need to be exactly where the problem is. So in this case, if we are looking for spigot wear on the cyclone, the sensor could be placed here. We could be detecting all sorts of things about that cyclone, but including the spigot wear, which is remotely away from the position of the cyclone. If we wanted to get more accurate information, we could add more sensors onto the cyclone and find positions of where the wear is exactly happening. And then these devices are powered by 5 volts DC. They're waterproof. They're in harsh environments. And this is the kind of example of where you can get this information on a cyclone and then look at the whole plant process and how one piece of equipment affects another. In terms of panels specifically, the important thing is that a panel with a sensor in it, like this one over here, is exactly the same as a normal panel. There's no difference. It doesn't need to be treated any differently. It gets installed the same way, and it then sends the data out wirelessly to a near field aerial that collects it and pushes that data to the cloud for analysis. This is what we want to avoid. By the time that happens, it's too late. We're getting misplaced material through those holes, and we can detect the level of wear on the panel and then also predict when that panel needs to be changed. So the goal is to change the panel one day before this happens. And the other stuff that we can do in terms of a panel with the same sensor is detect when a panel comes loose. First, one pin will come loose, then the second pin will come loose, then a third, and finally the fourth. So we believe that with one pin coming loose, we'll be able to detect it. Once the second one comes loose, it's very easy to see, and so on. We can find pegging, we can find the individual panel load. That would be very useful for working out how a screen works, and then looking at the whole screen performance, and damaged stringers and cross members could be an important part. Just an example of a real-time dashboard. We've showing here, so the timeline could be here at 7 o'clock in the morning on the right-hand side, and this data would be feeding across towards the left. And where this red and purple jump up is where Tramp came into 2 cyclones. So it's very easy to see alerts can be put on, emails can be sent. And this is an example again of a cyclone in a sensor on a cyclone in a real-time position. Lastly, I've got a couple of examples of how these sensors can be installed on equipment, and they can be bolted on, magneted on, glued on, and generally they're non-invasive and out of the way. Thank you.